Okay, good morning, ladies and gentlemen. My name is Stewart Whiteley. I work for a company called Petrenel, and myself and my colleague Anna Smith are going to talk about some aspects around global carbon CCS projects. So it's a broad subject, but so we thought we'd focus on three aspects. The economic evaluation of carbon capture and storage, CCS projects. So that'll be, I'll talk about that. And then I'll hand across to Anna, who'll talk about the environmental aspects and risks around carbon capture and storage projects. And then she'll talk about an interesting comparison between CCS and renewables, and is there a trade-off there? As a company, over the last 3 or 4 years, we've carried out 4 major CCS feasibility studies in 6 petroleum basins in different parts of the world. And what we thought we'd do is, the key challenge has been how do you economically evaluate a CCS project and rank different opportunities and different options. And the projects themselves can be quite complex mixes of storage in enhanced, use for enhanced oil recovery, storage in depleted gas reservoirs, and storage in depleted in deep saline reservoirs. So how do you evaluate that mix of possible opportunities? The approach we've taken is to look at the CCS as a business. And so we've created, conceptually a simple business model where you act as a CCS transport and disposal company. And basically you buy carbon dioxide or charge a company to dispose of their carbon dioxide. And you take that carbon dioxide and you'll take it to a disposal site, either sell it for enhanced oil recovery or put the stuff underground in either depleted gas reservoirs or deep saline reservoirs. So that's the business model. And basically by taking this approach, we can obviously look at all the inputs in terms of costs, the costs of the distribution system, the costs of the enhanced oil recovery projects. We can take into account different fiscal terms and conditions for different projects. And then at the end result, basically, the output then is a simple unit technical cost or unit disposal cost that then could be taken by, for example, the power plant company and factored into their decision on whether or not to proceed with carbon capture and storage. So that's the sort of conceptual model we follow in terms of trying to assess the economics. Of course, as part of the process in looking at the opportunities in the basin, the first step is of course to go through and screen the opportunities for storage. And maybe a mixture of storage in deep saline reservoirs, depleted gas fields, and of course enhanced oil recovery. So the first step is in looking at a basin, of course, is identify those fields that might be suitable for CO2 enhanced oil recovery. And so there's some screening to go through. Of course, you're looking at preferably CO2 flooding under miscible conditions, so that almost automatically dictates you're looking at oil fields, say, below 1,000 meters in depth. Preferably, the lighter the oil, the better. And of course, you're looking for reservoirs that have a reasonable permeability. So there's some screening criteria basically that we would apply to try and identify those CO2 enhanced oil recovery projects that might be viable. The next challenge then is, well, how do you work up some incremental production forecasts and CO2 utilization rates? And the approach we've taken, because we're doing very high-level screening, is to fall back to the United States, of course, where there's a wealth of available information. And we've developed a series of empirical models that allow us to predict what the incremental recovery might be, what the incremental oil production forecast might be, and how the utilization and the net import of CO2, net sale of CO2 to an enhanced oil recovery operator might look. So we've built some simple generic models that allow us to generate these production forecasts. And the first thing to note, of course, is that in most cases now, if you were going to employ CCS, you inject carbon dioxide into an oil reservoir for enhanced oil recovery. Within a few years, you're going to get CO2 back being produced through the well. So of course, you then got implicitly the need to recycle that CO2 to separate it out from its methane, put it back into the ground. And so the consequence is then that if you assume that's likely, then the net demand for CO2 to a CO2 enhanced oil project will go down with time. And so that's probably reflected in the red curve there. So the quantity that's going into storage goes down with time. If you've got a certain CO2 supply, of course you want to optimize that CO2 and put it into the best oil fields. And so you need to come up with some way of allocating that CO2 to the oil fields. And this is just, again, we've developed some simple programs that allow us to look at multiple oil fields and look at how the CO2 might be utilized in the oil fields. And this is an example, basically, where we've got 5 oil fields. I can't remember exactly in total how many million barrels of recovery, but typically about 200 to 300 million barrels of enhanced oil recovery. And with 2 or 3 big industrial plants producing, for example, power generation plants, what you see is that you need a lot of oil fields basically to use up that CO2. And because of the recycling of CO2, then it's not a complete solution. Basically, you can sell CO2 for enhanced oil recovery, for part of the project's life, but you'll then need to find some other sources or sinks to dispose of the CO2. And so inevitably, in nearly all the cases we've looked at for big industrial plants, you end up having to have some sort of combination. Ideally, of course, you'd like to put as much as possible into CO2 enhanced oil recovery, but usually you end up having to find an additional solution. Depleted gas fields, of course, are probably the best, but if not, then deep saline reservoirs. These are the incremental oil profiles. A lot of the work's been done at a very high-level conceptual level, and so part of the process, and of course, in working out the costs, is we have to have a networked pipeline system, basically to take the CO2 from the plant and then allocate and dispose of it in the different sinks. And because CO2 is liquid at above probably about 80 or 90 bars, then it's generally, of course, much more efficient to transport the CO2 in liquid form. And so inevitably you end up having to compress the gas, raise it up to probably in excess of 150 bars for delivery into the pipeline network, so that at the end, basically, you get out something that's probably in excess of 90 bars. So you're keeping it in liquid form. That minimizes the pipeline diameters and is the most efficient way to move the CO2 around. The next challenge is well, how many wells do you need? So often that's quite difficult because you've got, for enhanced oil recovery projects, you're dealing with old fields where there's often little data. So you don't know the condition of the wells, you don't know how many there are, and so you end up having to make some pretty generic assumptions in terms of what additional work you would have to do to convert some of these old oil fields that have maybe gone through primary and secondary depletion into something suitable for CO2 enhanced oil recovery. You also have to do some technical work to look at what happens to the excess, the surplus CO2 that you're not going to put into enhanced oil recovery. And this was just some modelling work, some modelling work that was done to look at disposal, how many wells you need to dispose of a significant gas stream basically into a deep saline reservoir. And this was just looking at how the CO2 migrated over 1,000 years basically from disposal in a deep part of an aquifer at about 3,000 metres. And of course it ends up migrating up dip into the tops of the anticlines. This was a nearby field basically that, so the question was, would you end up with any CO2 in that existing producing field? So that's the sort of technical work you need to do to try and scope out these projects. Having scoped out the projects, of course, then there's you have to go through, estimate the costs. And this is a selection of projects basically from around the world where we've worked up the costs basically associated with projects that involve a combination of CO2 enhanced oil recovery, deep saline reservoir disposal, and depleted gas fields. And just to give you, it's interesting just looking at the magnitude of the scale. I mean, this is cases H and I there, for example, involve offshore CO2 disposal, offshore CO2 enhanced oil recovery. And so there's, and typically something around about just over 1 billion barrels of enhanced oil recovery. So to, even though might sell CO2 to someone, someone else is going to have to convert their oil fields into CO2 enhanced oil recovery projects, and that's quite a massive capital investment in its own right. It's interesting that some of the other projects, if I can highlight some of these. So these are the sort of pure deep saline reservoir disposal costs, it's depleted gas field costs, and these are a mixture of depleted gas fields and deep saline reservoirs. Of course, you end up the lowest capital cost projects tend, of course, to be the depleted gas field disposal, because there you've got, if you transport CO2 at 90 bars, usually you'll find the stuff practically falls into the reservoirs, and it's only much later that you might need compression to pump up increase the injection pressure as reservoir pressures rise. So actually, the cost of disposal in, for example, some of the southern North Sea gas fields could be very low in terms of unit technical cost compared with the other options. This is just the same thing, I think, just showing the split in transport, storage and capture costs. And this selection of projects, we have excluded the capture costs. So this only looks at transport and storage. Of course, commensurate with the large capital investment, of course, there's massive operating costs to be factored in as well. And again, taking if you were to take the CO2 from 2 or 3 large power plants, basically, and try and sell it to operators for enhanced oil recovery, then they themselves would end up having obviously a massive capital investment, but also have to incur relatively high operating costs of many hundreds of millions of dollars per year. Just to finish off then, this is the output basically in terms of the unit cost of disposal. This is either, if it's a net cost basically, it's what would have to be charged to the power plant, for example, to dispose of their CO2, or if you're selling the CO2 to enhance oil recovery, you can make a profit, and it's the net profit you would make, expressed as dollars per ton of CO2. And remember, this excludes carbon capture costs. This only includes the transport and storage costs. But typically, you're looking at somewhere between $7 and $20 per ton if you were to dispose of CO2 into depleted gas fields or deep saline reservoirs. As soon as you can start adding the enhanced oil recovery opportunity, then you start getting into a position where you might be able to make some profit out of it. And in the very best, some of the best cases we've looked at, where you're typically looking at over 1 billion barrels of enhanced oil recovery, then you can start to make potentially some serious money out of this, with potential sort of profits of the order of $40 per ton. Just to finish off, this is just trying to look at the break-even price for the break-even volumes of enhanced oil recovery you might need to tip you into the balance where carbon capture and storage might be profitable under current prices and existing fiscal terms and conditions. And depends a bit on whether you're offshore or onshore, and the quality of the reservoirs and the fields that you're looking at. But you need typically somewhere between maybe 200 and 500 million barrels of enhanced oil recovery before you can start making a significant impact on this carbon capture storage business in terms of making it profitable. And of course, you tend to need much greater volumes if you're offshore or in poorer quality reservoirs than you do if you're onshore. Okay, so just to summarize then, so CO2 enhanced oil recovery, of course, has the potential to make CCS a profitable business. However, there's massive capital investment required, and to not only sort of capture and transport the CO2, but also to convert old oil fields basically to CO2 enhanced oil recovery. There's all sorts of things like replacing equipment, putting stainless steel pipelines in, and so on, separating out CO2 from the produced gas, re-injecting the CO2, and that all adds up and creates a significant investment. So typically 200 to 500 million barrels of CO2 potential will be required to economically justify a CCS project involving maybe, let's say, 2 or 3 big power stations. And that translates into original in-place volumes, probably around 2 to 5 million barrels. I mean, average recoveries for enhanced oil recoveries are typically about 12 to 13% from oil fields, maybe as low as 8, as high as 20, that sort of range. So you're really looking at, you need big oil fields and significant quantities of original oil in place, basically, to start justifying CO2 enhanced oil recovery in a greenfield site, in a greenfield area. What was also interesting is that when you go through this and look at the basins, that you find that you only need 2 or 3 big industrial plants to almost fully satisfy the CO2 enhanced oil recovery requirements. And so that immediately means, basically, there's a first mover advantage. Whoever gets there first is going to have an advantage. And of course, the examples, I guess, of states where you've got Kinder Morgan and Denbury, who have such a commanding control over the carbon CO2 enhanced oil recovery business in the States, that it's very difficult to break into that as a third party. Okay, that's all I've got to say, just to give you a bit of an overview of costs and how we might evaluate the economics and rank projects. What we'll do is take questions at the end. I'm going to hand across to Anna now, who will talk about the environmental aspects and the trade-off with renewables. Do you want me to?
Good morning, everybody. I'm going to be talking about the environmental impacts of CCS. Sorry. While CCS is recognized as an attractive sounding technology for mitigating CO2 from large point sources such as power plants, there are a number of negative impacts and risks associated with CCS which needs to be considered, and it is this that I will be focusing on in this presentation. I'm going to take a holistic approach to CCS and talk about the environmental impacts of the whole CCS chain, which include environmental impacts from coal mining. And I'm also going to compare CCS with renewable energy technologies. In order to prevent increases in global temperatures from exceeding a threshold of 2 degrees, a reduction of between 50 to 85% of global CO2 emissions by 2050 needs to be achieved. CCS could be used to achieve 15 to 55% of global carbon emission reductions necessary to avoid dangerous levels of climate change. For this, 100 CCS projects would need to be in operation globally by 2020 and 3,000 projects by 2050. Currently only 9 small projects are operating on commercial scale. Carbon capture requires the additional consumption of fuel, an increase of about 34%. Because of the consumption of this additional energy, the actual quantity of CO2 captured is reduced. The average capture of CCS technology, usually quoted, is about 90%. But for the whole CCS chain, which includes also fuel supply chain, the capture rate is reduced to around 72 to 78%. And if all greenhouse gases are included, this is reduced even further to 67 to 78%, depending on the technology and the type of fuel used. And including all greenhouse gases emissions, not just CO2, is especially relevant for coal and natural gas-powered stations because significant amounts of methane are created during production. There's oxy-fuel also quoted in brackets because this allows higher capture rates, but oxy-fuel is under early stages of development, and also production of pure oxygen is currently expensive and requires more energy. A study carried out in Germany shows that in comparison to CCS power plants, renewable energy generates only a fraction of greenhouse gas emissions. And these emissions from renewables coming mainly from the manufacture and construction of power plants. In addition to renewable energy, there are existing fossil fuel technologies without CCS, such as CHP, combined heat and power plants based on natural gas, which already achieving emission targets set for CCS technologies. Due to additional consumption of energy in other stages in the process chain, there would also be a rise in non-CO2 emissions, in particular those which can't be collected by the capture process. Non-CO2 environmental impacts associated with CCS include summer smog, eutrophication, which is when the environment becomes enriched with nutrients and disrupts the normal functioning of the ecosystem, soil and water acidification, and emission of particulates of less than 10 micrometers, which can cause adverse health effects, and even from the short-term exposure at elevated concentrations. The type of capture technology used will determine the magnitude of each of the above environmental impacts. The other direct impacts from CCS include the extra infrastructure required. And if the project was to be located in a tropical country, huge areas of a rainforest may need to be cleared for this. Sometimes CCS is presented as a clean coal technology, and whilst this may be applicable to mitigation of CO2, the environmental and health impacts associated with mining would still remain. Therefore, the indirect impacts of CCS would be the direct impacts from coal mining. And the reason I'm focusing on this is because the use of CCS would make the use of coal more acceptable. And instead of focusing on the mitigation of just CO2, we should be looking at the whole picture, and that is both direct and indirect impacts of CCS. This includes impacts on land, causing changes in landscape, such as destruction of mountains during surface mining, shown in the picture, creation of large slag heaps, water contamination, as mine tailing dams produce acid mine drainage, which can seep and pollute aquifers and rivers, air contamination from both coal mining and combustion, and health impacts from exposure to tiny particles of sulfur and nitrogen as a result of burning and mining coal. Coal combustion is also one of the biggest source of mercury emissions into atmosphere, which eventually falls back into the oceans and contaminates marine life and fish. And the costs of environmental pollution and effects on human health are not included in the cost of energy production generated from coal. If these external costs are taken into account, the cost of coal-based electricity would be a lot higher. Risks from geological storage of CO2 can be divided into global and local. Global are climate-related risks from release of CO2 into the atmosphere. Research shows that CCS would be effective in prevention of climate change, but only if leakage rate was less than 1% every 1,000 years. So, however, if the leakage rate was high, CCS may make things worse. As CCS requires more energy, this would lead to about 30% increase in CO2 emissions. In case of a well failure, all CO2 would potentially be released in a space of just a few decades, and which is represented by the first line in this graph. The other lines represent the number of years it takes before all CO2 stored is released under various leakage scenarios. So the question is, would less than 1% leakage every 1,000 years be a realistic goal? In a well-selected reservoir, the highest risk for leakage is via failed or deteriorated well. A few failed wells could cause the release of all stored CO2 in just a few decades. Long-term monitoring, maintenance and repairs of wells, especially offshore, is very expensive, and this would need to be carried out for hundreds of years. Realistically, would this be carried out in 50, 100 or 500 years' time? Even if CCS would help to avoid delayed global warming in the short term, if the rate of leakage is high, CCS would just defer the global warming to a future period. And in this case, what rights do we have to pass this to future generations? Local risks include human health risks, and these are potential impacts from either sudden high volume releases or from chronic low volume CO2 seepage. Natural concentrations of CO2 in the atmosphere is approximately 0.04%, and concentrations of about 7 to 10% of CO2 poses an immediate threat to human life. In the natural disaster shown here in this picture, about 100,000 tons of CO2 was released, killing about 1,700 people. For comparison, 100,000 tons of CO2 is equivalent to 1 week of CO2 emissions from one coal-fired plant. Local risks also include property risks, which is property damage, including to water or mineral rights, reduction of value of properties close to CCS sites, business interruptions for CCS operators if remediation is required, and resource damage if CO2 migrates to oil and gas fields and mineable coal. Financial risks include potential risks for returns, contractual liabilities, litigation expenses, and credit risks related to obligations for long-term operation and maintenance of CCS sites. Environmental risks. Often captured CO2 contains byproducts of combustion, such as nitrogen oxide, sulfur dioxide, and trace heavy metals. Their presence increases the risk of leakage due to their chemical properties. For example, when sulfur dioxide comes into contact with water, sulfuric acid is formed, which can dissolve the cement used to seal wells. CO2 also leads to acidification of water in the aquifer and can dissolve minerals and metals. Large-scale CO2 injection can have the potential to disturb regional groundwater flow systems, possibly displacing saline water formation to the near-surface environments, where it could contaminate shallow drinking water supplies. And if this were to happen, this would be quite a large environmental impact. Finally, as a comparison of costs of CCS with renewable energy technologies, assuming the earliest time large-scale deployment of CCS will take place is from 2020s onwards, would CCS be commercially attractive enough for the investors from 2025 to 2030? As this graph illustrates, initially the cost of renewable energy is dependent on technological factors and the assumed learning curves, while future electricity costs from fossil fuel plants will be mainly dependent by the prices of fuels and also CO2 price. The more research and development and investments are directed at renewable energy technologies, the quicker they will become more cost-effective than coal-based CCS. CCS plants in particular, due to the additional demand for fuel, would be dependent on future increases in fuel prices. The cost of generating onshore wind power and PV plants fell by 1/3 in the last 25 years, and similar cost reductions are expected for offshore power stations, with the greatest cost reduction expected to be in the next 10 years. Last year, renewables represented 60% of newly installed power capacity in Europe. A study was carried out in Germany to determine if renewable energy could be economically viable alternative to CCS. It showed that renewable energy could become more cost-effective than coal-powered plants with CCS by 2020 and 2030. For example, offshore wind energy would become more cost-effective from 2020, and gas-fired CCS plants. And from 2030, the whole mix of renewable energy could become competitive with coal-fired CCS plants. In conclusion, the role of CCS in climate protection is largely dependent on the timing of large-scale availability of the technology. The later CCS technology becomes available, let's say 2025, 2030, the less potential it has to act as a bridging technology for power plants. The benefits of CCS in capturing CO2 from large point sources should be weighed against its drawbacks, such as additional consumption of fuel, the increase in environmental impacts in the whole CCS chain, and the uncertainties and risks associated with CO2 behavior underground and CO2 leakage. More research and development is needed to close gaps in knowledge, such as long-term behavior of CO2 underground and its effect on subterranean strata. CCS does not solve the problem at the source. It does not reduce emissions, and instead it transfers them underground for future generations to deal with. Why should we be passing the consequences and burden from leakage to future generations? By the time CCS could be deployed on a large scale, other technologies with less environmental impacts and risks, such as renewable energies or CHP plants, could become more competitive. And in comparison, renewables solve the problems of CO2 emissions, and risks are known and are low. Thank you for your attention, and we will take questions if you have any.
Okay, any questions? And obviously this is for the whole presentation to Stewart or Anne, please.
Yeah, what about the supply of minerals that's required to make alternative energy technology, such as supply of rare earth? Has that
Such as what sort of supply?
Supply of minerals like rare earth. Have you considered that when thinking about when you're making a conclusion about the cost of alternative technology is going to be cheaper in the future?
I think in terms of costs and economics, then the answer is no. So we don't, I think, see that as a significant cost impact. But in terms of the relatively high-level screening we've been done, but from an environmental impact, Anna, do you want to?
I'm talking about comparison with renewable energy. So
Yes.
yes.
Oh, okay.
It's no. I'm not sure if this particular study has considered this, but yes, none of the technologies are without impact. So it's just comparing. If you were to take this into account, you would compare this with other technologies and just to see how, in comparison to others, it would what would the impact be. But yes, renewable energies also have impact, and this is the impact in this study. The life cycle analysis was done to show the whole impact from the whole chain, which includes construction of the power plant. But I'm not sure about what you talked about, the additional requirement for resources from minerals. I don't know if it answers your question.
Okay, anybody else? Yeah.
I'm Giorgio Caramanna from the University of Nottingham.
Yes.
I'm studying the effect of carbon dioxide on the environment. So about the Lake Neos example that you made.
Yeah.
That's true, but it should be say that the release was in a few hours, maybe minutes.
Yes.
So if there is a leakage from a real carbon sequestration area, is almost, or I say is totally impossible to have such kind of huge amount of carbon dioxide. So you can eventually have a steady release of carbon dioxide that will not affect population that way. I mean, it is a very particular example, I would say.
Yeah.
For example, there are areas where there is a natural release of carbon dioxide from a volcanic, are volcanic areas, mainly in Italy, even under the sea. I was studying that in the last 10 years. There is a huge release of carbon dioxide, but because of this, during the time, there is a sort of adaptation of the community. So I just would like to say that the Lake Neos example is very impressive, but is not very realistic because as leakage from storage site.
Yes, it's not long-term leakage, but if it's in case of the well failure, if the well was to fail, then this might be the case.
I think that's right. I think the other thing, of course, you're also transporting, going to be transporting CO2 under high pressure over long distances, and pipeline ruptures can occur. And statistically, it's probably very unlikely, as they've been operating for 40 years, CO2 enhanced oil recovery projects in the States without any major event like that. But there is the possibility of having significant short release, not reservoir related.
But even if you have a failure of an injection well, pipeline, even if you have a failure of an injection well, a pipeline, whatever, you cannot really have that kind of release. Because that was the old basic level of the lake, where there was dissolved CO2, by the way. There was a landslide, possibly triggered by an earthquake, that caused a sort of tsunami inside the lake. In that case, there was a huge release of carbon dioxide that you went from the dissolved phase in free phase. So I repeat, even if you have a blowout from a well, an injection well, you can have a huge release of carbon dioxide, and it depends, because if you're injecting as a supercritical, that will be not so huge. But even if you have a failure of something, it's not possible to have this huge amount of carbon dioxide released in so short time, and the village was down the slope of the volcano. So
No, we fully accept that, I think. But it is possible to get short releases that build the concentration up above 7%. So,
one more question, and then we need to stop for delightful tea and coffee.
Oh, let's see. Sorry.
Michael Priestnall, I just had a question on your 34% of energy used in CCS. I was wondering if you had any more information on how that number breaks down and under what sort of scenario for CCS that applies.
There is a range of figures used in various studies, which is about between 20 to 40%, with average rate of about 34%. But we need more time to if you would like, I can get back to you if you want to with more details if you're interested.
I mean, you need energy to compress the CO2, and then you transport it. You need to often boost injection pressures to get it into the ground. So there's whole additional energy consumption around moving the CO2 to the disposal site. And that's, I think that's where the bulk of that additional energy is required.
Okay, very good. Well, thank you both for your...
Okay,